Okay, so let's continue developing our formalism for general relativity. Now, I hope that you've taken part in the lecture series on classical differential geometry, because that really sets the stage for what we're going to do here. Okay, in classical differential geometry, we discuss holonomy, and we discuss the definition of the Gaussian curvature in those terms. And now we're going to do the same thing for Riemannian geometry, geometry of curved manifolds, no embedding space, intrinsic, okay, in the very same terms. So if you've seen this done for classical differential geometry, it's really a relatively easy step to accumulate. Okay, and again, we're going to be following a supplementary lecture 11, okay, which has all of the detailed indexology, which I really can't do in a lecture because I think it will just make people fall asleep. The concept shouldn't make you fall asleep. We're going to be developing the idea of curved space-time, and we'll be developing the Einstein field equations, and that's hot stuff. So let's talk about the curvature of space-time. In our course on classical differential geometry, we express the commutative of two components of the covariant derivative to calculate the Gaussian curvature. Let's do the same here. Okay, so what I want to do is look at the commutator of two components of the covariant differentiation and apply it to a 4-vector. Okay, I know how to do that. I know how the covariant differentiation applies to a 4-vector. It's naive differentiation, and then corrected for the fact that the basis vectors vary as I move through the manifold. Okay, so remember the idea here is to understand that parallel transport is dependent upon the path in which you choose. Okay, and so if I choose a path going from P to Q, in one case I can move along the mu direction of the coordinate system and then the nu direction. Okay, in another case I can move in the nu direction and then the mu direction. Okay, getting two ways to the path to the point P. Okay, the differentiation is path dependent, and so I'll get a different expression if I do it in those two different ways. Okay, and so let's look at that. I know that in a flat space, okay, this commutator is going to be 0. Okay, and examples have shown me that the commutator is different from 0 only because my space has intrinsic curvature. We showed that very explicitly in classical differential geometry, and we'll carry over those intuitions here. Okay, so this is where I like to look at it. In other textbooks, they might introduce the curvature by looking at a path that comes around and back to itself. Okay, and that's fine. Okay, and then we can look at the change of the vector along that path back to itself. Okay, the change of the vector is another vector because it's defined at the beginning point and the end point, which are coincident. I have an expression then for the change along a curve. It involves just my Christoffel symbols and the vector A integrated along that curve, and I can work on that and show that change in the vector is proportional to a quantity, which is in fact the Riemann curvature at that point P. And we'll be doing that here, and I like to do it here in terms of the commutator because that's a handier expression. Okay, so here's the commutator, here's the covariant differentiation, and I know how to take it. Okay, now I simply explicitly, no inspiration at all, I just slog through the left-hand side, take the covariant derivative, and take the other covariant derivative, take minus the covariant derivatives in the other order, and I'll get a result which is proportional to the vector I'm applying it to times the coefficient. That coefficient is guaranteed to be a tensor, okay? and it's the Riemann curvature tensor. And the result of all my arithmetic is that the Riemann curvature tensor looks like this: a gradient of a Christoffel symbol minus a gradient of a Christoffel symbol, and then the product of a couple of Christoffel symbols. And God help me if I get the indices wrong. Okay, so it's written properly in the supplementary lecture with the indices that way. The significance here is that my left-hand side is a tensor, right? These are all tensors in this expression. My construction is in a particular coordinate system, and so these particular pieces are not tensors. They're bound to the particular coordinate system and dependent upon it. But the left-hand side is a geometric object. All the nitty-gritty of my choices of coordinate system cancel out in these various terms, and the left-hand side is something very significant. We see that this is a Riemann curvature tensor. It's a 4-index tensor. It's fully covariant. It's 4-index tensor, so it has 4 times 4 times 4 times 4 components, 256 components. But in fact, only 20 of those are independent because there are various symmetries at play here. Okay. Okay. So that's it. That's the Riemann's generalization of Gaussian curvature from 2-dimensional surfaces to 4-dimensional manifolds. Okay. Okay. Well, in 2 dimensions, okay, there's only one measure of curvature, and that's a Gaussian curvature. Although there are many components to the that you might imagine, it all resolves down to one particular Gaussian curvature. And similarly, in 4 dimensions, you don't really have 256 components. Only 20 of them are independent. And why is that? Well, there are symmetries of the Riemann curvature tensor, which we can read off. We formulate the purely covariant Riemann curvature tensor like this by bringing that index row down. Okay, so that all of the indices are on the same line, or all the same, of the same importance. And then we examine our. We had an expression for the Riemann curvature tensor with one of the indices up. Now we have an expression for it with all of the indices down, and we can read off that there are various symmetries. Okay, so we read off, and I'm going to leave the details, okay, to the supplementary lecture 11, and just write them out. That it's antisymmetric in the first 2 indices. It's antisymmetric in the second 2 indices. It's symmetric if you change the first 2 indices with the second 2 indices, and then it satisfies some more sophisticated identities. If you have some row and keep row in the same position, but then cycle through the 3 other indices, you get 0. And then you have also the Bianchi identity, okay, which is that the covariant derivative on R, okay, and with these combinations is equal to 0, where again you cycle through the various indices. You see here, you leave the last 2 indices on R the same, alpha, beta, alpha, beta, alpha, beta, and then you consider the cyclic variation of the first 3 indices, and that's equal to 0. Okay, sound a little mysterious? They're not really mysterious. Look at the problem sets, and you'll find slick ways, okay, of showing that these identities are true. In particular, okay, you can typically go to the inertial reference frame, okay, establish them, write them in terms in a covariant fashion, and then you have them for all frames. And that's the slick tricks. And I'm leaving that to a recitation section and to homework to do that, because it's detailed work that isn't appropriate for this lecture. Okay. Now, once I have a 4-component Ricci tensor, I can make a 4-dimensional Riemann tensor. I can make other tensors of lower rank. Okay. In particular, I can make a Ricci tensor which is symmetric in its lower indices by contracting the upper index with one of the 3 indices that are lower in the Riemann tensor, and I've written it down here. Okay, and so that's called a Ricci tensor. It's symmetric, okay, as you can verify from the symmetries 1 through 3 that we had on the other page. Now you might say, well, why don't you make the other contractions of gamma not with the third one here, but with the fourth or the second? Well, you can easily see that because of the symmetries 1 through 3, that those other contractions are 0. So this is the only possible symmetric curvature tensor that I can make. Okay, it's called a Ricci tensor, and there you have it. Okay, so fill in the details by making those points concrete. Other contractions of antiquated symmetry, and then finally, if I have a Ricci tensor, which is symmetric in 2 indices, I can make a contraction. I can raise the index alpha and then contract it with the lower index and make myself a Ricci scalar. Okay, and that's fine. And then I can say a couple of words about that. For example, it can go back to 2-dimensionals, Gauss's world, and for 2-dimensional surfaces, only one component of the Ricci 4-rank tensor is independent. It's R1212, and we show in one of the appendices that in fact R1212 is nothing but the determinant of the second fundamental form. So we relate all of these Riemannian geometry constructions to constructions that we're comfortable with in the context of classical differential geometry. And we also show that the scalar, the Ricci scalar, okay, well, in 2 dimensions it has to be related to some scalar there, which manifests curvature. The only possibility is, of course, the Gaussian curvature, and so we'll find that they're the same up to a factor of 2. The factor of 2 is just a matter of conventions, and there you have it. If you're back to 2 dimensions, this whole development reduces down to something simple, and you can verify points 1 and point 2, and they're done in one of the problem sets. Okay, so now we can turn, once we have the machinery done, we can ask ourselves, what's the differential equation, okay, that replaces the Poisson equation for the Newtonian potential. In Newton's world, the del squared of the gravitational potential is just 4 pi Newton's constant times the mass density. This is just a differential expression of the more familiar fact that if you're outside a mass point, the potential falls like 1 upon r, and is proportional to the mass of the point and proportional to the Newtonian constant g. Well, we want to write that as a differential equation for the usual reason of our philosophy. The differential equations are expressions of the local properties of the theory. If I write down differential equations and then supplement them with boundary conditions or initial conditions, then I can solve any problem from that point of view. Okay, I don't want the integrated result. That's not fundamental. That depends upon initial conditions and boundary conditions, but the differential equation, of course, is fundamental. When we developed electromagnetism from scratch, we went back to Gauss's law, the statement that charge density is the source of the electric field. Okay, wrote that down as a differential equation, argued that if it's true for a static situation, it's true for a dynamic situation. If it's true for a charge that's sitting there, it's true for a charge executing any kind of motion, like accelerated motion or jerk motion. Okay, because when I write it as a differential equation, it becomes a statement of what's happening at that one space-time point. Okay, and so I can generalize from static situations to dynamic situations just by inspection. Integrating that differential equation, of course, is very complicated, but the statement of the differential equation is highly constrained by locality and causality, and I was able to make a lot of progress that way. Okay, now, so that's the statement from Newton. We want to transcribe that into the statement of interest to Einstein, and we remember from our discussion of the redshift that G00, the 0,0th component of the metric, is related to the potential in static situations by this particular formula, which is only true when V over C squared is small. Okay. The Newtonian situation. Okay. So we know that, and then we also know, we looked at examples of a fixed particle, and if it's moving very slowly, then we know that it has an energy momentum density, which is given by c squared times the mass density right there. Okay, and so I can rewrite this Newton's law in a way that makes a suggestion as to how to generalize this equation to relativistic dynamics. Okay, just with these definitions, Poisson's equation becomes del squared G00 is equal to a constant times T00, just by plugging in. Okay, so this result acts as a guide to the fully covariant Einstein field equations. Okay, this is true in Newton's world, well established by the observations of Kepler. Okay, it's sacrosanct. Okay, it should be true under static conditions and non-relativistic conditions. If I generalize this to strong gravity and highly dynamic situations, it should reduce back down to this, and so I use this as a guide as to what to expect in more general situations. Okay. So what properties should the field equations have? They're going to be a generalization of the Poisson equation from Newton. Well, of course, it should be generally covariant. It should be true in all reference frames. It should express the idea that curvature of space-time is proportional to energy, momentum, density. We've argued that case by various Canuncan experiments along the way. It should be second-order differential equation in G mu nu. Okay, well, the Poisson equation is the second-order equation, and we want to preserve that property. We want to preserve that property because the solutions of second-order differential equations are well behaved if you have sensible initial conditions. It should embody local energy momentum conservation. Certainly we want to embody energy momentum conservation into our theory. It should reduce the special relativities far away from the source of energy momentum. Okay, it should give rise to a flat Minkowski space far away from the source. Okay, it should reduce the Newtonian physics for weak static low velocity gravity problems. Okay. So naturally, on the right-hand side, let's look at the right-hand side first. We have G mu nu T00. Well, the natural thing to do is then to replace T00 by T mu nu. There should be a tensor, okay, there, the energy and momentum tensor, which generalizes, okay, the right-hand side to all situations. And it should be conserved. In other words, the covariant derivative acting on it, okay, should be equal to 0. And by acting on it, I mean that d mu T mu nu is equal to 0. Sum over mu, or sum over nu is equal to 0. A conservation law, okay, similar to a conservation law of charge in electrodynamics. This is now going to be the conservation of energy momentum instead. Okay, so the right-hand side, okay, we've dealt with that. What about the left-hand side? Well, the left-hand side should be a local conserved second-rank tensor. It should be constructed out of the metric and its first and second derivatives, and it should represent local space-time curvature. Okay, so I need a second-rank tensor. My energy and momentum tensor is symmetric, so this tensor on the left-hand side should be symmetric, and the Ricci tensor is the only one available. Okay, but it has to satisfy a conservation law. Energy momentum is conserved. Is the Ricci tensor conserved? To answer this question, I got to look at the covariant derivative applied to the Ricci tensor with the indices properly contracted. Well, to answer the question, I go back to the Bianchi identity. That's one of my symmetries of the Riemann tensor, okay, which I started with, and now let's manipulated it so that I have the covariant divergence of the Ricci tensor right? So I start with that statement of the Bianchi identity, and then I raise the indices as shown here, and contract the indices as shown here. So I involve the covariant derivative contracted against the Ricci tensor from the Bianchi identity. I get a bunch of terms. And I see, in fact, that the covariant divergence of the Ricci tensor is not zero. It's a half the covariant derivative applied to the Ricci scalar. So it doesn't work. Okay, but it doesn't. But it doesn't work in a way which is very organized. It suggests that, well, maybe I can make another tensor called G alpha beta, which is related to the Ricci tensor, by subtracting this character off. Of course, this character G, the Einstein tensor, will be conserved by virtue of this identity. Okay, so just apply d alpha to this fellow. Okay, you'll get d applied to the Ricci tensor, and then you get d applied to the Ricci scalar, and you see with this minus 1/2 in here, it's just right so that G is conserved. Okay, remember metric compatibility. Okay, the covariant derivative hitting the metric gives me 0. Okay, so that term doesn't contribute. I just get d applied to R and d applied to R. And I use this identity, and I get that the Einstein tensor G alpha beta is equal to 0. So this definition will be useful for us, that the Einstein tensor is related to the Ricci tensor by this term, which is just engineered in such a way that the Einstein tensor is conserved. Okay. Okay, and so there you have it. Okay, the greatest achievement of the human mind, written down in a simple way, motivated by foolish men. Okay, that the Einstein field equation is that the Einstein tensor is proportional to the energy and momentum tensor by these factors of 4 pi g over c squared, which are engineered in such a way that I'm going to get a Newton's laws when I go into non-relativistic momentum. Okay. Okay. So I want to direct you, of course, to the famous comments of Feynman, which sober us up. I mean, we found a way to motivate Einstein's equations, but God help us, no mortal would ever have found that path except for Einstein. Okay. And Feynman makes it very clear, expressing enormous gratitude to Einstein for being such a wonderful physicist. Okay. Don't think for a moment that because we did it with a couple of posters that anyone would actually find that path through the debris that really exists in all of this. Okay. It's really a miracle of intellect that we can do that. It's comparable to Beethoven's Ninth. It's comparable to Shakespeare's King Lear. This expression, one of the greatest establishments of science, and we'll find that out as we settle forth. Okay, so let's look at the technology here. Okay, in particular, we can write this equation in other different forms, which might be more useful for problem solving. In particular, if I look at this fully contracted form of the Einstein equations, just take G alpha beta and contract all my indices, then on the left-hand side, I'll get this contraction. On the right-hand side, I'll just get that contraction. If I define the Ricci scalar is a contraction of the Ricci tensor. If I define the energy momentum trace as the trace of the energy momentum tensor and write this out, I see that a consequence of the Einstein equations is that the Ricci scalar is proportional to the trace of the energy momentum tensor. That allows me then, okay, to go back to the Einstein equation, which is written out here, okay, and replace the Ricci scalar by T, the trace of the energy momentum tensor, and write therefore the Einstein equation in this form. So it's the Ricci tensor is equal to 8 pi g over c to the fourth. energy momentum tensor, and then corrected, okay, by this by a half t g mu nu, in order that the objects are conserved. Okay, and then we'll do a number of exercises to appreciate the Einstein tensor, and we'll do that next time. So take a look at this development. Okay, take a look at this expression of the Einstein equation. Make sure that you can get it from the original. Okay, because this is the one that I'm going to be using when I search for the Schwarzschild metric, the metric outside a spherical symmetric mass M. Okay, so we'll continue with this exercise the next time, and we'll be developing these ideas by looking at this equation and understanding some of its implications in a fundamental fashion before we turn to particular problems which are of interest to black hole